Hi and welcome everybody to the Fourier series analysis lecture. In last lecture we started briefly discussing about Fourier series analysis, and we said clearly that Fourier series analysis is used in order to write any periodic function in the form of exponential basis functions with some coefficients. And we studied the first form of the Fourier series analysis, where you can represent g of t as a summation of exponential basis function multiplied by complex coefficients. We call them c of n. In general, Fourier series coefficients Cn are complex numbers, even when the signal is real valued. Even if your signal is real, the output might be complex, no problem in that. The Fourier series coefficient can be computed by the following formula. Cn is equal to 1 over t naught, where t naught is basically the duration of one cycle of your signal, multiplied by the integration over one duration from a to a plus t naught of your original signal that I give to you, g of t, multiplied by the exponential 2 minus j2 by f naught nt. This integral is over any period of the signal. So a can be 5, can be 10, can be 100. But once you determine a, you just shift from a one period. Sinusoids have a finite number of terms. And by Euler identities, I of t can be written in the terms of cosine and sine. So it's equal to cosine t plus I sine t. And think of it like the x-axis and y-axis. The x-axis is always corresponding to cosine t, while the y-axis is always corresponding to sine t. Therefore, if I tell you write cosine t can be written in the form given below, is equal to e to power it plus e to minus it over 2, and sine t is equal to e to it minus e to minus it over 2i. In the exam, I can ask you to draw the coefficients, cn's. For example, give you cosine and tell you find the cn's of cosine, or find the cn's of sine. And cn's are complex numbers, so you can draw their magnitude and you can draw their phases on the two-dimensional diagram. The Fourier series coefficients for cosine are C0, C1, C2, C minus 1, C minus 2, from minus infinity to infinity. You will find, if you take this cosine t, yes, this cosine t, what's this? This is the function g of t in general. And put it here, g of t, you put it here. Cosine, you put instead of g of t, cosine t, and multiply it by e to minus j2 pi f naught nt, and integrate over a period from 0 to 2 pi. What's the period of 1 of cosine? 2 pi. And 1 over 2 pi. And find cn's. Everybody knows integration. Integration is from calculus. It's not covered in this lecture, integration, how to integrate. Integration is in calculus. So basically you integrate this by parts. What do you get? You get these values. That C0, 0, C1 half, C minus 1 half. These are the results of the Cn's. So you tell me the complex coefficients corresponding to cosine t are C0 equals 0, C1 equal half, C minus 1 equal half. What about sine? You just repeat the same process for sine, and you get 0, 1 over 2i, minus 1 over 2i for c minus 1. And I told you, what's the phase here? What's the amplitude? Let me ask you this. What's the amplitude of c1 here? The amplitude of c1 half. Take the amplitude of c1 half, yes? But what's the phase? The phase is affected by I, which is J, the complex. And when I in the denominator and you put it in the numerator, it becomes minus. I corresponds to 90 degree. So minus 90 becomes minus 90, minus pi over 2. Minus pi over 2 goes down. When you draw it on the two-dimensional diagram, it goes in the direction of the negative axis. Now, we have the example of square wave with period 2 pi defined over the interval from minus pi to pi, and we need to find the c-ends of this function. The most important thing to find c-ends, because once you find c-ends, you can put c-ends here with the exponential, and then you get the function. So basically, we know the basis function. The basis function e to power j2 pi, f naught n2. The only problem we have is the amount, the factor, the coefficient of this basis function. How much? We need to determine it. By defining these amounts, you define the resultant function, g of t. If you use different amounts, you end up getting a different function. That's the beauty of it. You have the same basis functions, you have exactly the same basis functions, and you just, this is the first basis function, for example. And this is the second basis function. And this is the third basis function. By determining C, the coefficient for the first basis function, and the coefficient for the second, and the coefficient for the third, you get different g of t. Because here, C1, let's say C1 is equal to half. And C2 is equal 0.7, and C3 is equal to 1. Half multiplied by this, plus 0.7 multiplied by this, plus this multiplied by this. Yes, from the summation, from the equation I showed you, this summation. This Cn multiplied by this, the exponential function into j2 by f naught is basically the sine. Sine but with different frequencies. Because as you increase n, the frequency increases. It becomes 2n, 2f naught, 3f naught, 3. That's why you have different frequencies. By defining these factors, you basically get g of t. You change these factors, you get a completely different g of t. So basically, this is how you do it. This is the magic behind Fourier series. You know the ingredients, which are the basis functions. You know them. These are the basic functions which are independent. Any function, you can derive it from them. But how? By defining these C's. Once you define them with the appropriate value, you can get any G you want. So if I tell you, this is a function. Could you please find the C's of this function? G of t, you just take this function, G of t, and put it inside the integration and find C-ends. Once you find C-ends, you know this function. So you tell me this function is basically the summation of this plus this plus this. Done. This is like synthesis. From these, you produce your final G of t, which is amazing. I mean, you start seeing what's behind the scene. This nice function that seems to be complex, I can divide it into many simple parts, many simple functions. And if I cannot find, if you are dealing with control or circuit or analysis or anything like this, if you take G of t as input to your circuit and you want to find the response of that at certain load or certain capacitor or whatever, you find it extremely difficult to find an answer for that, because the function you used as an input for your circuit is so complex, so sophisticated, so impractical that you cannot find a solution for your problem. One way to solve this is factorize your function into these basis functions. Simple. So instead of using that complex function, you just separate this big complex function into 3 or 4 or 5 simple functions, which are basically sines multiplied by coefficients, and find a response for your circuit for each one of them. And the total response is the summation of all of them. Very powerful solution. We call it superposition. Yeah, in circuit. Did you take that concept? Superposition analysis. You have kind of function that's composed of two inputs. You find this, and then you find the output. But you didn't know why are you using it or why should we use it. Because the function, when you took it in circuit theory, I think was trivial, like 5 plus 6. And when the voltage 5, what's the output? When the voltage 6, what's the output? What's the total output? Then the summation of them. But here you have complex functions that you cannot, there is no way you can solve it with G of t unless you factorize it into its own exponential basis function and find the response for each one of these exponential basis function, and that final result is the summation of these responses coming from each individual basis function. So this is for square wave. Square wave magnitude of t less than pi over 2. This means that, what does this mean? This means that between minus pi over 2 and pi over 2, you have 1. And above that, greater than pi over 2 or less than pi or minus pi, you have 0. You understand this term, mathematical one, how to write it. And then I told you find the Fourier series coefficient, Cn, you just come, Cn is equal to 1 over T naught. Yes, from here. Cn 1 over T naught. What's T naught here? Is the duration of your function, one periodic function, which is 2 pi. 1 over 2 pi from minus pi over 2 over pi over 2. Now, why from minus pi over 2 to pi over 2? Minus pi over 2 to pi over 2, how much? Pi. But the period is 2 pi. Why did I write it like this? Exactly, the other half is 0. So it doesn't mean, I mean, what would you integrate? The result would be 0. And then we put what's the function within this period? 1. And what's the e to minus j2 by f naught t? I told you 2 by f naught. What's f naught? 1 over 2 pi. 2 pi multiplied by 1 over 2 pi, they cancel each other. So you are left with what? E to minus j n t. And then basically here, calculus. You go back to calculus 1, calculus 2, integration, and you basically you must be very careful about the signs and minus and this and substitute them. And once you substitute, you will find this answer. Half sine pi n over pi n over n over 2. And we know that anything sine x over that value x is basically sinc function. That's why we define it sinc. And when I tell you draw it, you just say C0. What's the value of C0? Sine 0 over 0. Sine 0 is pi over, sine 0 is 0. Yes? Sine 0, how much? If I tell you find C0, you find that sine 0 is 0 and pi multiplied by n is 0. 0 over 0, undefined. What do? You go to the limit. You take the limit of this function and derive the sine. So it becomes cosine. Cosine pi n over 2 multiplied by the, and what's the denominator when you derive it? Becomes pi over 2. So when you substitute 0 inside cosine, what's the result? 1. Multiplied by half, you get half. Everybody knows, from one example, you are reviewing signal and system, calculus, derivative, limit theory, yes? From one example, in one solution. That's why I tell you this is so important. This is so critical. It links and connects 3-4 subjects together. Circuit, calculus, signal and system, and relates it to communication. You will see how this is related to communication. And then you find in similar manner, you find for C1, C2, C3. And then you tell me this is the C's, the coefficients of the exponential basis function. Clear? Now you tell me, okay, I had rect, yes, and if I get only one seized, one coefficient, which means one coefficient multiplied with one exponential basis function, what would be the result? I told you that the result, if we sum all the basis functions, after we multiply them with their coefficients, sum them, we should get g of t. What's g of t in our case? Rect. Yes, g of t is rect. And now after I found its coefficient c's, if I multiply c's with the exponential basis function and sum them all, I should get g of t, isn't it? Now, this is a demonstration to show you what will we get. To show you the effect of number of terms, the effect of number of c's on your end result. Let's say you get only one c's, c1, and multiply it by the exponential and draw the function. The function will look like sinc. Is it close to rect? Nobody would recognize that this is close to rect. If I tell you take three terms, three c's multiplied with their exponential function, what would be the result? The result would be this, which is a little bit closer. If I tell you take 5 terms, you will get this, a little bit closer. If I tell you take 7 terms, you will get closer. If I tell you take 100 terms in MATLAB, write it, what will you get? You will get very close to the function, but still you have these ripples, oscillation around the top and the corner. And we call this phenomena Gibbs phenomena, that you cannot always, if you have rect and you find it c's, you cannot exactly take certain number of coefficients, multiply them with the exponential basis function, sum them, and get the exact g of t. Correct. You cannot. This is to do that, you need to take infinity number of terms, and in our practical world, we cannot take infinity number of terms from minus infinity. So since it's close enough, we accept to stop at 100. It's fine. It's no problem. And we call the most important point that I want you to see with me is the fact that we are able to generate almost rect from the c's, we found multiplied with their exponential. The other important point is that no matter how big the number of terms we take, we will always face the problem of Gibbs phenomenon. Gibbs phenomenon states that the function you get from the summation of your exponential function multiplied by the coefficient cannot be exactly matching with g of t, which is rect. And the reason for that, because to do that you need to take infinity number of terms, and this is impractical. However, since it's resembling the original function closely, approximately, so we take it. We limit the number of factors and we take it. Especially in transmission. In transmission we use rect, and rect in time corresponds to sinc in frequency. So sinc keeps oscillating to infinity. So to avoid the interference totally between your band and your friend's band, you must wait to infinity to cut this. But you cannot wait to infinity. Can the transmitter keep waiting, waiting until you cannot? Time is a limited resource. You need to transmit quickly. You cannot tolerate too much delay. So due to this, since you cut, when you cut, you cause interference because you didn't take the whole energy. You didn't represent the function accurately. But what we do, we put some bands, guard bands, we put some filtering, windowing, so that we reduce the interference. Now, there is also another form to represent any periodic function. The first form was g of t is equal to summation of cn's multiplied by exponential. But I already told you that the exponential e to minus j2 by can be written in the form of cosine and sine. Yes, this function. This is the first form. G of t summation of cn's multiplied by e j2 by f naught n. Now instead of e j2 by f naught nt, from Euler identity, you know that this can be written in the form of cosine plus sine. So basically, you just do this, the same. You come here and you put it, g of t now can be written in the form of cosine and sine, which is equal to half a naught plus summation from 1 to infinity a n cosine 2 by nt over t naught plus summation b n sine 2 by n naught. Did you take this form in signal and system? This is the form you talked about in the previous course related to signal and system. Did you talk about the previous form, this cn's and this? Did you understand their relationship with the function and how they are basis function related to each other and this? So basically, it's just to confirm the importance of this concept. So why didn't you answer me when I asked you about Fourier series analysis? Why did we use it and how to use it and what's the relationship? How did you get this physical meaning of Fourier series analysis before? That you can not only math how to do it, but the physical meaning of why, how are they related to the function and how are they really the ingredients, and you just need to determine the amounts so that you get the function. Did you get this concept? So you are clear about it now? You were not clear before, now you are very clear about it. That's the point that I want to make. I already said in the previous lecture, we understand things from 3 perspectives. First, by words, second, by equations, third, by visualization and the drawings. If you link these together, you become really understanding what you are doing, and you reach to the level where you can produce new knowledge. But if you just memorize and you just repeat and just know how to do this, but why you don't know, and what's the relationship between the equation and the drawing you don't know, or how to explain it in words. If you know these things, you become able to generate new ideas. You become Einstein, basically. You understand me? You become the next Einstein who's able to generate new knowledge. If you understand the why and link the equation with the drawing with the words. So you are not anymore a student. Trust me, you are not anymore a student. You can generate idea. You can, while you are reading and go home and study, you can say, okay, this equation, what if we do that? What if we do this? I think it can be improved. It can work as well. It can, yes, you start questioning. I think they are wrong. I think this doesn't make sense. How are they teaching this in the schools for these many years? You must start out questioning. And once you reach that point, you are crazy, unstoppable. I mean, you become really able to, come up with something new once you reach that point. And already your friends, they already did this. They already came up with new things. Your friends in 4th year and 3rd year, they were able to come and published in top journals in the world. And students like you just made them believe in themselves, and they started questioning, and they came up with the new modulation schemes, and they accepted by the experts in the world. So it's normal. Once I put you in that phase, you become Einstein. He's not better than you. But if you want always to just care about how and don't care and just the grade and this, you will always be normal. Be normal, okay. You don't know the why. If you don't know the why, you don't know why are you here. You don't know what's the relationship between this and that and the drawing and the equation and the word and why this happened, how it comes. You cannot dare to question anything. You take everything as if it is like holy. Why? there are concepts might be in the books that are wrong. Question them. Try to find mistakes in what you are reading, in what you are studying. Always, always. So this is the second form of Fourier series analysis, and how to find ANs. Here we don't have CNs. We have ANs and BNs. AN, you can find it by this equation, 2 over T naught, integration of GT, cosine 2 by F naught NT, and BN the same, but you multiply it by sine instead of cosine. A third compact form combines the sine and cosine terms into phase-shifted cosine terms. So we have not only two forms, but also the third form, which is g of t is equal to C0 plus summation from n equal to 1 to infinity an cosine 2 by n f naught t plus phi n. Basically here, the sine and cosine, you transfer them into phase-shifted cosine. Cosine with phase shift, because there is a relationship between cosine with phase shift and sine and cosine. Each frequency component is described by amplitude and phase in this case. Which form do you like to go with? Personally, which form do you like to go with? I think the complex form CN is the easiest and most straightforward one. Because see how many terms here to find them. Why are you making it so complex like this here? And here you need to go to the geometry equations in math. So I think this is straightforward. This is handy. Yes. And CN's complex number already has the AN and BN, and more relevant to frequency because you have real and imaginary, and you just draw them, you get the answer. Now, having understood Fourier series analysis, now I assume you expert in Fourier series analysis, expert in why we use it, expert in what does it mean, expert in how is that related to practical world and physical world, and you can even calculate it for any function. Now, we give you a brief introduction about the different types of systems. For theoretical and practical reasons, we restrict our attention to systems that have useful properties and represent the physical world. So basically signals, there are too many types of signals, and we are keen to understand the signals that are causal, continuous, stable, linear, time invariant. What's causal? Since you know signal and system, what's causal? Yes, ones who know signal and system. What's causal system? Causal signal. Causal signal means the signal depends on the current and the previous values only, doesn't depend on the future values. What's continuous? Takes any value within a certain duration. Stable means it converges to determined solution. So if you have a decaying function as an input to your system, the output is also decaying. Linear, exactly. If you have a system, the response of the summation of two functions is equal to the sum of the responses of each individual function. This is a linear system. So the response for A plus B is equal to the response of A plus the response of B. What's time invariant? It doesn't change over time. It remains with the same behavior, with the same characteristics. We are very interested in understanding and dealing with linear time invariant system. And because linear time invariant system are, we encounter them in the physical world frequently, and they are practical to some extent, and they satisfy the following properties: impulse response and the transform function. W of t, if you have linear time invariant system, you have the input V of t and the system H of t, the output W of t is the convolution of the input and the system. And in the frequency domain, WF, the Fourier transform of W of t is equal to H of f multiplied by V of f. So basically you take the Fourier transform of each signal, yes, and it becomes multiplication instead of convolution. Signals as vector. Can you represent signals as vectors? I think you can, because signal basically, what's it? Signal is kind of a function. Yes, and especially if it is discrete, you have at specific values, at specific samples or specific time instances, you have determined values. So you can put these in a vector form. Yes, where a signal g of t defined for a finite number of time variables. G of tk is equal to gk for k from 1 to n. Can be considered to be a vector of dimension n. G, see how I wrote it? G is small letter and bold. Bold small letter means vector. Bold capital letter means matrix. So here you have, in this vector, what do you have? G1, G2, Gn. Think of it like the first column in a matrix, or the first row in a matrix. This is the signal. When you draw these points, you get function, signal. You connect between these points, you get function. So what do we care when we have a signal in a form of a vector? What do we care about? To find the norm of that vector. We call it the Euclidean norm or magnitude of that vector. How do you find the magnitude? Very easy, straightforward. Square root of the first element square plus second plus till infinity, and you take the result, which is this. Everybody knows this from math, everybody can calculate it. And it works for complex valued signals as well. If G1 is complex, also you do the same. Amplitude square plus amplitude square and take the square root, this is the magnitude. Also, we care about the norm. The norm. How is the norm related to magnitude? Norm is equal to magnitude square. You remove this square root basically. Yes, the norm is used, and norm is very important to measure how far apart are two signals from each other. Why do we care about that? Because when we transmit in communication, when we transmit our signal at the transmitter, it goes through the channel. The channel affects the signal, makes it noisy. What does this mean, noisy? Means it's difficult to understand its shape. You receive it, you don't recognize it. This is not the signal that I transmitted. So, to see how far this signal is from the original signal, you take the norm. You record your signal and put it in a vector, and the signal you transmitted, you put it in another vector, and you subtract them from each other, and then you take the amplitude, magnitude, and then square it. This is the norm. The value here determines how good your received signal is. Where is your received signal in this example? G hat. And the original signal you transmitted, G. And this we call it square error. Our goal in communication to minimize this as much as we can. Orthogonality of two vectors. When do we consider two vectors orthogonal to each other? If 90 degrees between them. But in math, what does this mean? The dot product between them is 0. What does it mean? Dot product takes into the first vector magnitude, the second vector magnitude, cosine. If the angle between the two vectors 0, cosine 0, Yes, cosine 90, yes. If the angle between them is 90, cosine 90 what? 0. So the orthogonality satisfies when the dot product is equal to 0, which means the angle is 90 and in words orthogonal, they have perpendicular shape. How do you prove this in math? From Pythagoras. Magnitude of f square plus magnitude of g square, if it is equal to magnitude of f plus g all square, this means they are kind of orthogonal. No, this is general. This is general. This definition general. If you have this term f dot g 0, then they are orthogonal, which is the dot product. Thus, two signals are orthogonal if and only if inner product is equal to 0. Inner product, the dot. In general, dot product is equal to magnitude of the first vector, magnitude of the second vector multiplied by cosine, where theta is the angle between f and g. If theta is equal 0, then f and g point in exactly the same direction. If it is 0, means the angle, they are in the same parallel to each other. If theta between 0 and pi over 2, they are like this. F and g point in the same general direction with an angle less than pi over 2. If it is minus pi over 2, f and g are perpendicular. If it is pi over 2, they are also perpendicular. If theta between pi over 2 and pi, then f and g point in opposite general direction. One in this direction and the other in that direction. If theta equal minus pi, then f and j are in opposite direction. So this is regarding the orthogonality of two vectors. For most signal processing application, the number of samples is much larger than 3. The number of samples. So we cannot easily visualize signals as vectors. In fact, n might be infinite. Example, tk, k delta t for k 0, 1, 2, 3, or even k from minus infinity to infinity. When the dimension is infinite, the signal's norm may be infinite. Yes, if the signal has too many values going from minus infinity to infinity, then the norm can be infinity as well. But if the norm of your signal, which is the magnitude of g square, equal to summation of the elements square is less than infinity, we call it energy signal because the energy is finite, and we say it belongs to L2. Yes, the energy of the sample signal depends on the sampling interval delta t. The power in each interval is gk magnitude squared, so total energy is, this is the magnitude of your signal, magnitude of g of k. When you take the square, it becomes power, and when you multiply it by the time, becomes energy. We already explained it in the previous lecture. If the sample interval of your pulse of your sample goes to 0, we obtain a continuous time signal with energy given as limit of summation, limit of this basically. If the width of your sample goes to 0, becomes continuous basically. The class of finite energy signal is named L2. All the signals which have finite energy, we call them L2, norm 2 signals. The two major tasks of signal processing are estimation and detection. Estimation, you need to know how, you need to be able to estimate and get close approximation of what you have transmitted. finding a good estimate g hat of t of unknown signal g of t you transmitted. Your data is unknown, yes? G to the receiver. Receiver job to be able to know g of t, yes? The signal, the message, the voice, whatever. So basically, you are trying to make a good estimate of what the transmitter sent to you. So you want g hat of t as close as possible to g of t. This is what we call it estimation. So you try to find the parameters that when you fix them, adjust them, you get accurate estimation, signal without errors. Detection means identifying which one of a finite number of possible signals is present. Again, based on the signal that depend on g of t. So basically, in communication system, let's say you have v of t, which is the message you are transmitting, and you send it over the channel, h of t, it gets convolved with it, and there is a noise added to it, and you received z of t. Z of t is what you received at the receiver. What's the job of the receiver now? To be able to know what's v of t. But there is noise and there is channel. He needs to eliminate the channel. How? By estimating it and cancelling it, dividing over it, and try to predict the signal and not predict, estimate the signal in the presence of noise as accurate as possible. So it's a difficult task. To do that, we use mathematical formula, mathematical derivation, and optimization, and many techniques in order to be able to predict our signal correctly. So basically, suppose you have your transmitter is sending a QPSK where your data bits are mapped into 4 different symbols, which can be 0.7 plus j 0.7 and minus plus plus minus 0.7 plus j 0.7. Okay, 4 different symbols. Nice. You transmitted them over the channel affects them, the noise affects them. So instead of receiving 0.7 plus 0.7 j plus or minus or whatever, these are points. We call them discrete values, determinate finite set of values. Instead, you received 0.5 plus 0.9. What's this value? This is after estimation. After you tried to remove the effect of the channel and the effect of the noise. 0.5 plus 0.9. In which quadrant? In the first quadrant. So you say, this is, you already done with the estimation after removing the effect of the channel and the noise. But now you need to detect it. You don't have 0.5, 0.9. You only have 0.7 plus 0.7 j and all the different terms, plus or minus. So, to which quadrant you will consider this point? You will consider this point as 0.7 plus 0.7 j because 0.5 real in the first quadrant and 0.9 j also in the first quadrant. So positive x, positive y. And 0.7 plus 0.7 j, positive x, positive y. So most probably it's this point that the transmitter sent to me. Yes? But how much was the error in estimation? Minus 0.5 minus 0.7 and 0.9 minus 0.7. This is the estimation error. So you want to reduce this as much as possible. A simple example of a channel with noise results in an output. Assume this is X, your vector data that you want to transmit, and the channel is C, and this E is noise, and this what you receive, G. Where the gain C and error are unknown. In estimation, you don't know the channel, you don't know E. There are infinitely many solutions To minimize error, I tell you what's the value of C. The value, you don't know the value of C, you don't know the value of E, and you want to know X from G. Is it possible in math? In math, you want to know X, but you don't know E and you don't know C. How is that possible? To know X, at least you need to know two variables. You know G, you received it at the receiver. But you don't want G, you want X. But X is manipulated with C and E. How would you find? So you go to the estimation. To do that, if you want to solve this mathematically, there is infinity number of solutions. You don't know which one was true, which one actually the data that the transmitter sent. Yes? There are infinity many solutions. To minimize error, the error in estimation, we put E is equal to G minus Cx. And we keep trying different values of C and X that minimize the error. Yes, but this again is not a realistic solution. The component of G along X is magnitude of G cosine theta. Therefore, G becomes this, the dot product between G and X is basically magnitude of X, magnitude of G cosine theta. So we can solve for C as the dot product between G and X over magnitude of X squared. This formula, this C value, applies to continuous time signal. Suppose G of t is defined for T1, for the duration between T1 and T2, we can approximate Gt by Cxt. The energy of the error in this case is equal to the integration of G of t minus Cx of t squared, magnitude squared. To minimize this error, you derive with respect to C, and by doing so, you can find the value of C. So basically, as you can see, the estimation process and the ability to find a good estimate while you are unknowledgeable of two different variables, which we call them C and E, is a difficult task. Especially in practical system, noise, you cannot know it. There is no way you can learn noise. But the channel, you can train it and learn it. So in communication, we have one of the problems that we always face whenever we transmit our data and want to receive it correctly. The problem is that my received signal is the channel multiplied by X plus noise. Now, if you want to know X in math, what do? First, you subtract E, then you divide by C to get X. Is that true? In communication, we do the opposite. First, we divide by C, and then since we don't know E, we keep it and determine X. Does this make sense to you? It's against math. Math says if you have a variable multiplied by something, added to something else, and you want to find X, the first thing you need to do to get rid of the plus and addition, subtraction and addition processes, yes? And then division and multiplication. But in communication, we cannot do this. We just divide immediately by C, and we ignore that there is E. And this causes a very problematic situation to us in detection. It increases the noise, and therefore we cannot detect our data perfectly. Why? Why is that? I would love in the future a scientist come from you and be able to solve this problem. find a solution where we can first subtract E and then divide by C. Why do we do this in communication while we know the rules of mathematics? Because we don't know E. E is noise. Noise is random. Since you don't know it, can you subtract it? You cannot. So you assume that it's not there. But C, you know it, you can learn it, you can train it. You divide by C. But when you divide by C, if C is small, E over something small gets larger. So you enhance the noise, you improve the noise more. It affects your system more. That's the problem, the trade-off. This is a problem in communication, open problem. So we would love to be able to solve it. Application to signal detection, for example, radar system. Consider a radar pulse G of t, and you send this G of t, the pulse, to the air, and when it hits something, after a certain period of time, you receive a reflected signal. Here, let's say, this says that there is an object that's far from me, this distance, and moves with this velocity, just by receiving this signal and analyzing it. So basically radar has two functionalities. First, you can detect whether there is an object or not by this signal and system. And second, you can say how far this object, what's the speed of that object, and how should you shoot it or stop it. Imagine? So, well, how do you do that? Once you receive the signal, the return signal depends on whether the transmit signal encounters a target. Here, Wt represents noise and interference. Y of t is equal to A G of t minus t naught. If it is like this, then there is a target. If it is Y of t only, which is noise, then there is no target. How do you determine whether there is target or not? You correlate between the received signal and the signal, the pulse you transmitted. If there is, with different shifts, if the correlation is not zero, this means there is a target. If the correlation is zero, this means no target. So when you do, correlation is basically like dot to product operation, W of t, G of t minus t naught. Here, is there a target? W of t says target absent, no target. When you integrate W of t with G of t minus t naught, basically what you transmitting, but shift it at different time because it takes some time for your signal to reflect and come back. You get the result zero if there is no target after you get the integration. But if there is a signal reflected, not W of t, you have G of t minus t naught with A. What's A this? A is the attenuation, basically less than 1, to tell you that the signal after it goes forth and back, its amplitude is no longer the same. It's shorter in the amplitude. But I care about the correlation. If there is correlation, the correlation is not zero, then target is there. And not only this, you can also determine the distance from time, the time it takes from the signal to go from here to there and return back. And you can determine the velocity. And accordingly, you can track the object. This is how radar systems work. Obviously, we decide based on whether the correlation is non-zero. To detect targets at all possible distances, we vary t. So this is basically the part related to signal and system, which is very critical to understand the communication principles and the modulation concept in this course. So with this, we conclude our lecture and we stop here and continue in the second part after a while. Thank you very much.